scan design. So how we are implementing the scan register using the transmission gate. So now, so this is a scan register. So a scannable D flip-flop can be constructed by adding a multiplexer to the D flip-flop. So already in third unit, we have implemented the multiplexer based latches using the transmission gate. So for 2:1 mux, so we need two transmission gates. For the D flip-flop also we have implemented using the transmission gates and the inverters. So for 2:1 mux, that is the two inputs are D input for a D flip-flop and the scan input, scan in SA. So this is the implementation of multiplexer using transmission. So in scan design, the concept is when scan, that is the control signal is scan, the scan is asserted, the data input is loaded and it is connected in the shift register and at last it is shifted out. So this is the control signal for the scan register and the SI is nothing but a scan in and the SO that is scan out. So for this implementation scan, so it is asserted means scan is equal to high. So if scan is high, so what will happen? Scan is high, the bottom transmission gate is on, so that is scan in is connected to the register. So we are loading the data input to the register and it is shifted out. For example, scan is low. So scan is low, the top transmission gate is on. So it is like a normal D flip-flop. That means D is available on the Q output. So this is the implementation of scan register, that is a multiplexer, and this is the implementation of ordinary D flip-flop. So usually in the transmission gate implementation, at the input and output we are using the inverters. That means we are isolating the output from the noise. So for that we have to connect inverters at the input side and the output side. And this is the tri-state inverter. So tri-state inverter means the inverter followed by the transmission gate. So inverter and the transmission gate is nothing but tri-state inverter. So instead of inverter and the transmission gate, we have connected the tri-state inverter. So this is the whole implementation of D flip-flop. So in scan register, we have D flip-flop and the multiplexer. So in this, the setup time increases by adding the delay of the extra transmission gate. So this can be reduced by using clock gating concept. So clock gating is nothing but stopping the clock to the unused portions of the chip. So clock gating circuit consists of AND gate. So the input is clock and the one more input is latch enable, that is enable input. So this is the circuit of clock gating. So for this circuit we are applying the clock gating to the unused portion of the chip to reduce the delay. That means we are expecting the same setup time used in the D flip-flop, ordinary D flip-flop. So this is the circuit for clock gating we are applying to the scan register. So the one of the signal is phi, that is equal to clock, and one more input is scan in. So this is the clock gating. So this clock gating concept is applied to the implementation of scan register. So now we have separated the D flip-flop and the scan, that is scan in input, and if it is not used, so we can stop the clock for the circuit, and if the scan in is not used, we can stop the clock for the circuit. So using the clock gating, we are stopping the clock for unused portions of the chip. That means we are expecting the same setup time in the ordinary flip-flop. So this is the concept of scan design, serial scan, parallel scan, and the scannable register design. So the next method in DFT is built-in self-test. So as the name suggests, it relies on augmenting the circuits that allow them to perform operations upon themselves that prove the correct operation. So it consists of the analyzer, signature analyzer or the cyclic redundancy check. And the advantage of BIST is it adds the area to the chip for the test logic and reduces the time required for the test logic and also lowers the system cost. So this is the advantage of BIST, and it consists of the signature analyzer or a redundancy check, and this involves the pseudo random sequence generator. Pseudo random sequence generator, PRSG. So this can be constructed using linear feedback shift register. LFSR. So linear feedback shift register is nothing but a simple shift register with feedback from two or more outputs to the input. So this is the linear feedback shift register, and this can be implemented, that is constructed by using flip-flops. For n-bit shift register, we need to connect n number of flip-flops. So and the XOR gate. So now we'll discuss how the LFSR is implemented using the flip-flop. Then we'll generate the pseudo-random sequence. So built-in filter is nothing but we are generating the pseudo-random sequence that we are going to apply to the combination logic block. Then at last we are going to calculate the syndrome. So that syndrome will be verified with the correct syndrome. So whether the circuit is good or bad. So this is the construction of 3-bit LFSR. So this is a symbol. Actually, in simplicity, we can draw this diagram. And so we have 3 number of flip-flops. We are taking the output from Q of 1 and Q of 2. It is connected to the XOR, and the output of XOR is connected back to the input of the shift register. So for example, so we have so this is 3-bit. So we have 2n minus 1 number of states. For n-bit shift register, we need 2n minus 1 states. That means n is equal to 3. So 2n minus 1 is 7. So it consists of 7 states. So it is not applicable for all 3 outputs. So we are taking from 0, 0, 1. So first we have to do the XOR operation for 0 and 1. So it is 1, and we have to do the 1-bit shift. So it is 0, 0. Then we are taking 1 is out. Again 1, 0 is 1. Then shifting 1, 0. So again, so we are generating the pseudo sequence, random sequence, and again 1, 0, 1. So 1, 1. So it is 0. 1, 1 is 0. Then 1, 1, 1. 0, 1, 1. 0, 1. Again 1, 1, 0, 1, 0. 0, 0, 0, 0, 1. So 1, 2, 3, 4, 5, 6, 7. So we are totally 7 states. Again we are repeating the same sequence 0, 0, 1. So it will go from 0, 0, 1, again 1, 0, 0. So for n bit, so we need 2n minus 1 states. So it is not applicable for the 0 states. So for that we are going for complete feedback shift register. So that means n bit LFSR can be constructed and converted into the CFSR by adding n minus 1 input NOR gate to the circuit. Okay. So we will consider the CFSR. So this is the structure of complete feedback shift register. That means we have taken the output from Q of 0 and Q of 1 to the NOR gate. This is the other symbol of NOR gate, and we are not considering the last bit of the output. So for this complete shift register, complete feedback shift register contains 3 bits. So it is a 3-bit register. So already I said for testing we are generating the test pattern generation by using pseudo random generator. Then we are going to apply this input to the combination logic. So at last the signature analyzer, the blocker signature analyzer will get the input from combination logic. Then we will calculate the syndrome. So for best process, first we need to reset the syndrome to 0. Then it is XORed with the output on every cycle. So at the end of the sequence, the LFSR, so LFSR contains the syndrome, which is a combination of all previous outputs, and it is checked with the previous, that is the correct syndrome, to check whether the circuit is good or bad. So this is the process of BIST. So now we'll draw the BIST diagram with respect to the linear feedback shift register and the NOR gate, 2 input NOR gate. So this is the structure of BIST 3-bit register and how it is used in the system. So in the BIST consists of the combination of signature analysis and the scan technique. In this we have modes of operation that is based on the signal C of 1 and C of 0. So if it is 1 0, all the flip flops. So all the flip flops are initialized to 0. That is the reset mode. And if it is 1 1, so C of 1 and C of 0 are 1 1, it looks like a ordinary D flip flop. And for 0 0, that means C of 1 and C of 0 is equal to 0 0. It behaves as a scan mode, that is 3-bit scan register for the input, and if it is 0 1, it behaves as a test mode. That means it will generate the pseudo random sequence and the signature analyzer will calculate the syndrome. So this is the test mode. So if C of 1 and C of 0 are 0 1, and how it is used in the system. So again already I told you that. So it is consists of pseudo random sequence generator and the signature analyzer. That means the output of this generator giving to the logic block, that is the combination logic block. The signature analyzer will get the input from this combination logic. So in summary, the BIST is performed by resetting the syndrome and it is calculated by the signature analysis. It will get the input from the combination logic and it is checked up. That is, it will check at the last, so whether it is good or the circuit is good or bad. So this is the concept of design for testability. So three methods: ad hoc testing, scan design, and the BIST. So the applications of BIST are, it is used in WLAN, that is wireless LAN modem chip. So it consists of 1 million gates. So in that we are using this scannable register. So it consists of the architecture BIST. So the next topic is shifters. So shifting operation is essential. It is used in the floating point units and the scalars and the multiplication process. So in this we have two types of shifters: barrel shifters and the logarithmic shifters. But in our syllabus we have only the barrel shifters. So first we'll discuss how we'll perform the 1-bit left or right shifter. Then we'll move to the barrel shifter. So these are the structure of 1 bit left or right shift programmable shifter. So in the so based on the control wires, that is a left or right, no operation. Based on the control wires, the input word is either shifted left or right or remain unchanged. So this is a 1 bit, and the multiple shifter can be constructed by cascading the 1 bit left or right shifter, but it is very complex and it is long, and also the process is very slow. So for that, the commonly structured shifters are called barrel shifters and the logarithmic shifters. So in barrel shifters, we have constructed that is 4-bit barrel shifters. Then we have the data lines. So we have the data bits A3 to A0, and the control wires we have SH0, 1, 2, 3. So the control wires are routed diagonally, and the number of rows equals the input data line, and the number of columns equals the shift width. So the input word length is 4. Again, the shift maximum, that shift width is 4. The control wires are routed diagonally so that the input word is shifted right. So this is the right shift. This is the structure of barrel shifter. So from this, we have completed the unit 4. So in unit 4, we have discussed about the data path circuits. So in data path, we have the adders. So adder, first we will discuss the binary adders. Binary adder is nothing but a full adder, and the full adder is implemented using the static and the dynamic. So the static adder, dynamic adder. Then the high speed adders carry bypass and the carry select. So these are the high speed adders, and the carry lookout also you have discussed. Then these are the adder circuits. Then multiplier. So we have the 4 cross 4 array multiplier. Then the array multiplier and the carry save multiplier. So using vector merging adder, we constructed the carry save multiplier. So these are the array multiplier structure, and the other multiplier structures are both multiplier. So in both multiplier, we have used radix for that is radix for coding, that is both multiplier and the Wallace tree multipliers. These are the other multiplier structures. Then the shifters, so 1-bit left or right shifter, then barrel shifters. Again, the last topic is testing. So how what is the need for testing and the design for testability. So we discussed the 3 methods. So these are the 4th unit. So next class we'll discuss about 5th unit. So these are the assignment questions. So what is the memory BIST? So in BIST we have for on-chip memories. So we have the architecture for the memory circuit and draw the equivalent circuit of clock gating. That is what is the circuit for clock gating and implement the D flip-flop using the transmission gate and give an example for pseudo-random sequence generator. And in testing, but one more testing also we have, that is IDDQ testing. So IDDQ testing is nothing but a supply current monitoring. That is a testing for a supply current. So if there is any bridging faults in the circuit, so we can measure the supply current on a VDD line. That is supply current on VDD line. So IDDQ is nothing but VDD supply current Q-cell. So that is what IDDQ testing. So when CMOS logic is not switching, that means it draws no DC current. But due to some bridging faults, so we have a DC current. So DC current that we have to measure using IDTQ testing. That is available on the VDD line. So it can be tested externally or internally. So external to the chip by measuring the supply current on the VDD or internally by using the test circuit. So this is the concept behind IDTQ testing. So this is also available in the testing concept. Just 5 minutes.
So good morning. So in the previous sessions we have